Okay, now we look at the example 4. Okay, so you have to evaluate the line integral along the helix. So now your curve is in 3D system because you have the component x, you have the component y, and you have the component z. And the limit of t also provided 0 to 2 pi. So we use the same procedure where you have to find the ds in terms of dt, then you have to find the velocity, the speed. Okay, so r prime differentiate negative 4 sine 40, 4 cos 40, and then 1, and then we find its magnitude. So 16 sine square 40 plus 16 cos square 40 plus 1. So we can factorize the 16 when you have sine square 40 plus cos square 40 plus 1. So we know that from identity this is always equal to 1, and we will get square root of 17. Okay, and then we can find the definite integral in terms of t, where you have to obtain the x squared plus y squared. So x squared is cos square 40 plus sine, y is sine 40, so sine square 40, and then plus t squared. Sorry, that is only x squared plus y squared, so there is no z. Okay, and then ds is so what is ds? ds is r, the magnitude of r prime, dt, where from your magnitude just now we have square root of 17 dt. So you can replace your ds square root of 70 dt. So t is from 0 to 2 pi. So using the identity, we know that this one is equal to 1. So then our integration, we got a simple integration. So just the integration of square root 17 dt, 0 to 2 pi. So square root 17 t 0 to 2 pi, and you will get square root of 17 to pi. So that is your answer of this particular line integral. Okay, so that is the line integral for scalar field. When everything you have to convert into t, okay, where the information provided is in terms of vector function, in terms of RT. But sometimes you can just convert your line integral in terms of only x or in terms of only y. Okay, so that is the thing that you want to look in this section. Line integral with respect to only x, or with respect to only y, and with respect to only z. Okay, so in some application, the following line integral with respect to x arise. So instead of with respect to arc length, so we can also the line integral with respect to x, with respect to y, or with respect to z. Okay, so for this particular case, so this is an integral over some curve C in 3 space. Okay, so for this particular integrand, because we have x, y, z, so this is the integral over the curve C in 3D system. Okay, so then how can you convert? So last time, if you have ds, so you use the formula of speed to convert into dt. But if you have only x, how can you convert into only t? Okay, so now look at here. If you have the line integral respect to x, so we just obtain the derivative of x or component, and immediately you have dt. Okay, if you have respect to y, so how can you have dt? So you just find out the derivative of y component. But if you have z, then how can you have dt? Your integration in terms of respect to t, so you just find out the derivative of z. Okay, so now look at the example 5. Example 5. So you have, okay, look at the A. We want to obtain or evaluate the line integral where you have x squared plus y with respect to only x over the curve C. So the curve C here, C is the portion of the parabolic curve, and along the parabolic curve, it's starting from the point of 0, 0 to the point 2, 4. Okay, so now you have the with respect to x, so now we want to convert in terms of t. Okay, so you have to have the, if you want to convert everything in terms of t, then you have to imagine, okay, imagine now your curve is a quadratic, and the point, the initial point is at 0, 0 to 2, 4. Okay, so that is your curve. So meaning that you have to erase other lines. So we don't interested on this, and also we don't interested on this, only that curve. So that is your C. So that is your C. Okay. So you have to have the, in order for you to convert everything in terms of t, then you have to obtain the vector function of the quadratic. Okay, so the simplest one, because we know that the parametric equation is non-unique, but we so normally we will start with the simplest one, where we equate x equal to t and then y equal to t squared. So that is the simplest parametric equation of the quadratic, y equal to x squared. So that is your r, and now you have to determine the t. So now look at your point here. So what is the t? So that your x0, your y0. So again, determine the value of t, so that your x0 and your y0. So it looks like your initial point is at t equal to 0. So this one when t is equal to 0. And then for this one, what is the t for you to have t equal to 2 and what is the value of t so that your x is equal to 2 and your y is equal to 4. So we can see that when t is equal to 2, so your x is 2, your y is 4. So your t is from 0 to 2. Okay, so now you have to convert the x squared plus y in terms of t. So x is t, right? This is x is t, so x squared is t squared plus y is t squared. Okay, and then your dx, how can you convert into dt? So you have to differentiate x, and you have to have dt. So your x is t, so differentiate the t, you will get 1 dt. So your dx is dt. So t from 0 to 2. And then when we simplify, you have the 2t square dt, 0 to 2, and 2 over 3 t cubed, t from 0 to 2, and then 2 over 3, 8. So you have 16 over 3. Okay, so this is how can you evaluate when you have a situation, you have the line integral respect to in terms of x, not ds. Okay, instead of, actually there is another way. Instead of you convert everything in terms of t, you can, I think there is a way which is, I think, more simpler. So now I copy the original integrand, okay, for the curve C. So now I change everything in terms of x, because you have a dx here. Now because we know that y is equal to x squared, so I have square root of x squared plus, so what is y from the curve given? So y is x squared, right? So I have x squared dx. So now everything is in terms of x. So now I have to, so based on your curve, so now what is the limit of x? So because we have to integrate respect to x, and everything is in terms of x, so now you have to be able to find the limit of x. So now look at your point. So we just focus on the x component. So you have 0 to 2. So your x is 0 to 2. So 0 to 2. So you have 2x squared dx, 0 to 2, and you have 2 over 3 x cubed, 0 to 2, and you will get the 16 over 3. So your answer is the same, and looks like this, the second option here is more simpler. Okay, both are correct, but this one is more tedious because you have to obtain the vector function of this curve. But this one you have to replace, because this is dx, so you have to convert everything only in terms of x using the curve provided. Okay, and also because you only convert in terms of x, so you have to be able to find the limit of only x. So we ignore the y. Okay, now we'll look at the second question using the same curve. The same curve but different line integral. So now we look at the B. So the line integral we have is okay, integrants the same but with respect to y. So we have the same curve. So now that is your curve. So let's say here I want to convert everything in terms of y. So since we know that from the given, because we have the same curve, right? So this is the information for the curve provided, where we know that y is equal to x squared. So we want to have y is x squared plus y dy. So what is the limit of y for the curve? So now we look at the limit of only y. So the limit of only y is 0 to 4. Okay, 0 to 4. 0 to 4. So you have 2y dy, and you have y square 0 to 4, so you have 16. Okay, so now in the notes, I provide you the step. If you convert everything in terms of t, you can try that. Because we already have the RT here, so we will use the same RT because we have the same curve. And using that in terms of t, we obtain 16, where the answer is the same if you just use something in terms of y. Okay. Okay, so there is a property, a useful property, which is additivity. So let's say you have a curve is made by joining a finite number of curves end to end, then the integral of the function along the curve C is the sum of the integral over the curve that make it up. For example, you have your curve is given by the combination of very many lines. So let's say you have this one, and after that you have that one, and after that you have that one. That's it. Okay, so because now the first path given by C1, and the second path is given by C2, and the third path given by C3. So your line integral, let's say in general you have this one for the curve C, when you know that the curve C is the combination of C1 plus C2 plus C3, so you have to compute the line integral for each curve. So the line integral along the C1 plus the line integral along the C2 plus the line integral along the C3. So that is called the additivity. Okay, so this is for I'm explaining the additivity property.